Hello there, and welcome to a video about 1.1.1 structure and functions of processors. So the first topic you need to know is what is a processor? And a processor is a processor executes instructions which allow programs to run. So this is a processor right here. It's the Apple M2, and it's processing instructions which allow programs to run on the computer. So we need to know a bit more about processors. So what's the contents of a processor? You have the arithmetic logic unit, which is inside the processor, and it executes all arithmetic and logical operations like arithmetic operations such as mathematical operations like plus, minus, times, and divide, and bitwise shift operations. And then for logical operations, you have things such as Boolean logic and comparison. So then you also have the control unit, which is also known as the CU. So this may be known as the ALU, arithmetic logic unit, ALU. And the control unit is also known as the CU. So the control unit directs the operations of the CPU. So it directs the flow between other devices and the CPU, and it's responsible for coordinating all the activities of the CPU. It's in charge of accepting the next instruction, decoding it, and then sending those results back into main memory. That's the CU, so the control unit. And then inside the CPU, you also have things called registers, which are small memory cells that are really fast, and they are used to store data. There's 5 types of registers. You have the PC, which is the program counter. You have the ACC, which is the accumulator. You have the MAR, which is the memory address register. You have the MDR, which is the memory data register. And you have the CIR, which is the current instruction register. And you have the program counter, where it holds the address of the next instruction to be executed. So the next instruction can be, the address for the next instruction can be in a sequence, or it can be like an instruction, like an address to jump to a different instruction, completely. And then you have the memory address register, which holds the memory locations where data or an instruction is to be fetched to or written to. Then you have the memory data register, which temporarily stores data that is going to be read from or written to. You also have the accumulator, which is a general purpose register, often used to store temporary data from things such as the ALU. So all the arithmetic and logical operations calculations may be stored in the accumulator. And then you also have the current instruction register, which holds the current instructions that are going to be executed. And the thing it does, it decodes the instruction, so it splits it into opcode and operand, which equals the decoded instruction. You also have the system bus, which is a set of parallel wires inside the CPU which connects things together. And there's 3 buses within the CPU. You have the address bus, data bus, and control bus. And together, they're known as the system bus. So let's get started with the data bus. The data bus is a bidirectional bus, so that means it's sending and receiving. It carries the binary 1s and 0s that make up information being transmitted around the CPU and the computer. And then you have the address bus, which is unidirectional, which means one side, and it carries the memory addresses that are identified from where data is and is being written to. Then you also have the control bus, which is another bidirectional bus, where commands and control signals to and other components are sent from the CPU and other things. And you also need to know for this topic what is assembly. You don't need to know. We're not going to be going through all of assembly in detail in this video, but it will be covered in a later video. Assembly language basically uses mnemonics to represent instructions. So it's like a simplified way of representing machine code. And here's the assembly language mnemonics you need to know for A level, but we'll be going through that later. It doesn't really go through it in this one. So you need to know what the fetch, decode, and execute cycle is. And the fetch, decode, and execute cycle is like a sequence. So like imagine a circle, like the water cycle, something like that. It's like a sequence of instructions that are completed. So an instruction can be executed. And you have 3 different phases. You have the fetch phase, decode phase, and execute phase. With the fetch phase, you first the address from the program counter, which is the PC, is copied to the memory address register. Instructions held at that address is copied to the MDR via the data bus, and then simultaneously the contents of the program counter are increased by 1. And then the value in the memory data register is then copied to the to the current instruction register. And from there, in the decode phase, the current instruction register, like we said before, splits the instruction, decodes it, so it's split into opcode and operand, so it's decoded. And then in the execute phase, we just execute the decoded instruction. You also need to know what pipelining is. And pipelining is the process of completing the FDE cycle of 3 instructions simultaneously. So executing 3 instructions at the same time, kind of, while holding the necessary data in a buffer near the CPU, such as the accumulator. So while one instruction is being executed, a different one is being decoded, and another one is being fetched. And this is done by separating instructions into instruction pipelining and arithmetic pipelining. Instruction pipelining separates the instruction into fetching, decoding, and executing, and arithmetic pipelining works by breaking down arithmetic operations and overlapping them as they're being performed. The main goal of pipelining is to reduce the amount of time the CPU is left idle. So, like in this diagram right here, while one instruction is being fetched, another one is being decoded, and another one is being executed. We also need to know what factors affect CPU performance, and there's a few things that can affect CPU performance. One of them is the number of cores that your CPU or processor has, and a core is kind of like an independent processor, capable of performing its own FDE cycle. So let's say you have a dual core processor like an Intel dual core. That means theoretically it can finish tasks 2 times faster, and so on and so forth. So like my personal computer, it's an Apple M2 computer. It may have like 8 cores, I believe. I can't remember, but yeah. You also have the amount of cache memory. So that's the onboard CPU memory, often used to store temporary data like the accumulator. And there's like different types of cache levels. So inside the CPU, there can be level 1, level 2, or level 3 cache, and their properties are completely different. So level 1 cache is like very fast memory cells with small capacity. Level 2 cache is basically relatively fast memory, between 256 kilobytes and 2 megabytes. And level 3 cache is much more larger, but it's very slow in comparison to level 1 and level 2. You also have the clock speed, which is determined by the system clock. And it's like an electronical device inside the CPU that generates signals between 1 and 0, and all operations begin on the pulse of the clock. So kind of like a heartbeat. It goes from 1 to 0. The clock, the higher the clock speed, the faster the pulse, which leads to faster performance. That's why there's so another thing we need to go through is different CPU architectures, and you have the von Neumann, which in this diagram as well. the von Neumann has basically all the components, the basic ones, like the control unit, the arithmetic logic unit, the registers, and the memory units. But there is shared memory space for instructions and data, and instructions and data are stored in the shared memory space. It follows a linear FDE cycle, which means one instruction at a time. Then you also have the Harvard architecture, which basically has the basic components just like the von Neumann architecture, but instructions and data are stored in different memory units. And each memory unit has its own system bus, reading and writing data at the same time as fetching and decoding. So it's mostly used by RISC processors. That's the difference. Instructions and data separately, kind of. And then you also have things like modern architectures, like contemporary architectures, which you have SMID, which is a single instruction, multiple data, which is a form of parallel processing that carries out a single instruction on multiple data items at the same time. This is often done with like GPUs. Then you have a MID, which MIMID, which is a multiple instruction, multiple data, and multiple instructions are carried out on multiple data items across multiple cores. And then you have distributed computing, which is using multiple computers over a network that are working together to solve a really big problem. So, like a current example right now is like AI. You have ChatGPT, which is done, all the processing is done on multiple computers at the same time. And that's the video. So I hope you enjoyed it. Thank you so much for watching.